Hello, everyone. Thank you very much for your joining us today for the AIAA Los Angeles Las Vegas section meeting. It's a hybrid meeting on May 21st, 2022. Today, we are honored to have Professor George Bibel as our distinguished lecturer. Is a very renowned professor in mechanical engineering from University of North Dakota. He's also AIAA distinguished lecturer. Is very knowledgeable, and he has book published. He thinks about this black box, and he has a new one with a certified pilot from Boeing, Airbus. So there's a lot of very exciting things that will coming out from today's lecture and discussion. So the lecture itself is 45 to 50 minutes. Okay, so afterwards, please ask some questions. This is great opportunities. And for people local here, if you order the lunchbox, it will arrive at 12:15. So depending on the Q&A and see how it goes. All right. So if any question, please welcome, just speak out. But please, if we have major question, please wait after the lecture, the presentation. And you can raise hand or speak out during the Q&A session, but maybe let the professor finish her lecture first. All right, so without further ado, let's welcome Professor George Bibel.
Thank you for inviting me. The title of my talk is Loss of Control. It's the most common crash scenario. I'm going to give a few examples and try to give common features. I'd like to introduce myself a bit. I'm now an emeritus professor at the University of North Dakota. I worked with NASA quite a bit, and I attended the Airline Pilots Association Advanced Accident Investigation course, ALPA. I'm also a Boeing consultant. I wrote 2 books. First one was developed in a short course presented at Boeing several times. They actually talked about presenting it to all their engineers, but the real crash investigators got jealous and shut me down. Now, a few years ago, the crashes were so few, especially in the United States, it was easier to talk about it on a more casual basis. They're obviously in a different place right now with the 737 MAX. The second book was co-authored with a certified Boeing/Airbus captain. He was attracted by the first book, and I was able to connect with him. He gave important contributions. He's allowed to write a book on crashing airplanes, but needless to say, his airline doesn't want anything to do with the subject. So we can't use his airline's name. My books have fared well on Amazon. First one had 54 ratings with 4.8 out of 5. The second one slipped a little bit, but it also contains this rating, 1 out of 5 stars, by someone who never read the book, who's complained about the price. So a single star cancels out 10 5-star ratings, given a ranking of 4.6. I've given over 30 sponsored talks, including MIT, Cornell, Johns Hopkins, GE Engines, United Technologies, Boeing, NASA. And my books are in libraries at the FDA and FAA libraries, all the service academies, West Point, Annapolis, etc. Numerous United States Air Force bases, all significant engineering schools, Naval Research Lab in the U.S. Army Aviation Technical Library. The point of my books are to be interesting, insightful, with entertaining information, at least entertaining for engineers. Most people don't want to talk about plane crashes. And it's also anchored to simple explanation of engineering concepts. The world doesn't need any more engineering books nobody can understand. Seems to me they're just too in love with their advanced math and won't think about simple explanations, which is really what I spend most of my time on. Now, you guys here initially asked me to comment on China Eastern Airlines Flight 5735. It's a Boeing 730-800 that crashed March of this year, killing all 132 people on board. My initial response was a resounding no, because we can't trust early reports and the media badly distorts rumors. Now, this plane crash just made some recent news just a couple of days ago. Wall Street Journal had a report from unnamed sources. I'm going to describe that later when I lined it up with another accident that had massive bad reporting examples. And I'll link the two of them together so we can compare them. I'm not saying the Wall Street Journal is wrong, but it certainly sounds like these other unnamed sources that were very, very wrong. So instead of talking about a recent crash that doesn't have current information from the investigators, a better approach is to comment on historical facts that might be related. So we can look at a few historical examples. And I'm also going to make a big deal about bad reporting because it's so pervasive. And I even have first-hand experience with bad reporting. I've been interviewed a lot on cable news. Newspapers like the New York Times, New York Post, Magazine, Scientific American, Popular Science, and C-SPAN. I have nothing but contempt for the process because the reporters are so bad. You tell the producer what you want to talk about, then you get on the air, and it's a random conversation. They have no knowledge whatsoever of what they're talking about, make no effort to be informed. The written media plays out a little differently. I think it's part of the reporter's creed not to report what you say, but to interpret what they think they heard and understood. So it's really totally misrepresented because basically they don't understand engineering information and they won't admit it. And don't forget, CNN asked if the missing plane was lost in a black hole. So can't get any worse than that. I normally like to start with a few dramatic images. Big planes are struck once per year on average. A thunderstorm is a big deal. It can destroy all planes with the winds. But it's basically a small plane problem because small plane inexperienced pilots get lost and wander in the thunderstorms. Plane hasn't been destroyed by a thunderstorm in the United States since 1963. It's basically it hasn't happened since modern weather radar. The big jets easily avoid the thunderstorms. So there's really two different problems, the high-speed winds and the lightning strike. Now, they had a lot of problems with the composite 787. They had to completely redesign it to get the electricity to flow through it, because the electricity flows through the epoxy composite differently. Here's another dramatic picture. Note the tires on fire. It's a 150-year-old technology used on ship construction. As soon as they start using iron ships. One big problem is riveted construction can cause arcing. So the Titanic has over 3 million rivets, had over 3 million rivets. It's a big deal when they replace riveted ship construction with welding in World War II because of the reduction of labor. We've never been able to do it with planes because welding degrades the metal fatigue properties. So the problem is if you have a loose rivet head, creating a small gap, the electricity flows through it and arcs. If the arcing is inside the fuel tank, it will ignite the fuel vapor and cause an explosion. So you insert the rivet with one head shown, and then you bang on the other end to create the second head. In addition to just better fabrication techniques, they also have a backup safety features. They have flame sensors. If they sense any bright light, they'll blanket the area with nylon blanket to snuff out any fire before it explodes. In fact, there's stories of it being so sensitive that it's been triggered by inspectors' flashlights. So FAA made Boeing relocate the rivet heads from the inside of the tank. This is a normal fabrication method to the outside. So if there's any arcing, it doesn't affect it's not inside the fuel tank with the dangerous explosive fuel vapors. And I normally like to go through my dramatic pictures of wake turbulence. There are literally horizontal tornadoes coming off the tips of the wings. A DC-9, 77,000 pound DC-9 got flipped over and crashed flying 2.5 miles behind a 330,000 pound DC-10. At that time, they increased the spacing from 3 miles to 5 miles. And a couple of small planes have been broken up in flight getting too close to big planes. And it sets the throughput on busy airports. You can't take off too close behind each other. This is another shot from the same photography. It can be a factor in loss of control. This is a wind tunnel image. It's connected to the last big US crash, an Airbus A300 I'll talk about eventually. So they're horizontal tornadoes coming off the wingtips. You got hard pressure underneath the wing and low pressure above. So the airflow curls around the wingtip from the bottom to the top of the wing. I'd like to define loss of control and do some statistics. This Boeing puts out this annually. They only look at planes 60,000 pounds and bigger. They've been putting this out every year since 1959, which is considered the start of the modern jet age. This Sky Library link up here has 20 years of it, from 2001 to 2020. It's a MAX 737 crash, October of 2018, March of 2019. Boeing skipped their annual report in 2018, 19, 20. The latest report was delayed till September of 2021. So they skipped 3 or 4 years with the MAX 737. Airbus recently started putting out a similar report in the last 10 years or so. So I'm going to assume Boeing is waiting for more 737 MAX flights to reduce the crash rate. The metric is basically crash per million flights. So those numbers are going to look terrible in the near term for the 737 MAX as they deliver more planes and have more flights. The crash rate will improve dramatically. So this is from the last Boeing report on big plane crashes. So the vertical axis is fatalities. So loss of control has the most fatalities. So there's 8 loss of control in the plot I just showed you, which is 20% of total accidents and 37% of total fatalities. Those are major pilot air categories. Uncontrolled flight into terrain. It's kind of the exact opposite of loss of control. The plane is totally under pilot control. There's a loss of situational awareness. They lost track of where the mountain is or where the ground is. But it's certainly piloted air unless there's some kind of instrument failure, which is extremely rare. So that controlled flight into terrain is 15% of total accidents and 14% of total fatalities. Another pilot air category is runway excursions. Basically, they missed the runway. That's 18% of total accidents and 8% of total fatalities. They mostly occur on landing, where they land long and end up off the runway, or they land short before the runway. They also occur on takeoff, where they just fly off the end of the runway. So total pilot air for big planes, according to Boeing statistics, are 53% of total accidents and 59% of total fatalities. There's an international committee that reviews these accidents and assigns categories to them, which is what Boeing is using. Some of the other causes, equipment failures, they broke it out by power plant and non-power plant, and some of them together because they're both kind of small. So they're 10% of total accidents and 17% of total fatalities. Here's a few other categories. Unknown is 7.7%. Fuel lights, fire, and ground handling are small numbers. And it's mostly considered a non-US problem. In this one study, there was only one US loss of control out of the 22 accidents they studied from 1999 to 2008. So there's like 7 or 8 big studies out there. We just grab a bunch of crashes and study them and assign patterns. So there's a couple of them. The most common way they define a loss of control is significant departure from controlled flight outside the operational flight envelope. Unusual flight attitudes, which is normally defined as greater than 25 degrees pitch up or 10 degrees pitch down, or a bank angle of greater than 45 degrees. It's really more complicated than that, because everything I just said, those are one-axis rotations. So obviously an airplane has 3-axis control. It's a rudder, elevators, and ailerons, and you can have 3-axis rotations combined. So you talk about being out of position, and if they're in trouble, it rapidly turns into this kind of situation where you have multiple axis rotation. Going through my list of loss of control definitions, inappropriate airspeeds, which mostly refers to stalling. So here's a summary. And incidentally, small planes have 100 times more loss of control accidents. Now, a lot of that, of course, you have a lot more small planes than big planes. But still, there's a significant difference because small plane pilots simply just aren't trained as well as big plane pilots. This is the first loss of control accident I'm going to talk about. Kenyan Airways Flight 507 happened in 2007. It's a Boeing 737-800 Sydney to China plane just crashed. And everybody on board died. This also gives me a chance to talk about bad reporting. Before the plane is even found, nothing announced on where the plane is. New York Times reports the plane is 155 miles from the airport they took off from. Washington Post reports it's 100 miles from the airport. It turns out the plane is found 3 miles from the end of the runway. It crashed shortly after takeoff. What happened was there were thunderstorms in the area. So local people heard a lot of thunderstorm noises, and they reported it as a plane crashing. And the reporters just passed along without really any verification to understand what they're talking about. 3 days after the crash, the Los Angeles Times report engine failure was focus of the investigation. That never happened as far as I know. It's not in the report other than the standard superficial references. The investigators found numerous procedural errors, such as they had no pre-flight plan to avoid thunderstorms, which is a fact that they think they weren't paying attention enough because they had their heads buried in the weather radar. The pilot calls for a before taxi checklist. The co-pilot starts the before takeoff checklist. They couldn't even agree on what checklist to use. No one noticed. This is my favorite procedural error. They took off without asking for or receiving permission from air traffic controllers. Imagine that they're sitting on the runway. They just suddenly decide to take off without talking to controllers at all. The plane had a tendency to roll right. It's caused by manufacturing misalignments, which would be considered normal. The roll was easily corrected for the first 4 seconds of flight by turning the control wheel to the left. They tried to turn on the autopilot and failed to notice the autopilot did not engage. So the next 55 seconds, the plane is flying itself. It's either on autopilot or under human control. Why did the autopilot fail to engage? Well, they don't really know, but the 2 theories in the crash report are the pilot simultaneously nudged the control column, and the Boeing logic gives preference to the human operator. And this accident plane had several autopilot system failures, but it passed 2 inspections before the accident. So just 24 seconds into the pilot this event, the plane had banked 24 degrees and changed heading by turning 25 degrees. And nobody noticed. So again, the working theory is they're trying to maneuver through storms and had their head buried in the weather radar and weren't paying attention to the rest of the instruments. Remember, the procedure calls for a pre-flight plan. So from the report, during the pilot last 55 seconds, the flight crew demonstrated lack of rigor in piloting, confusion in autopilot use, and poor situational awareness, pointing out where the navigational display, including weather radar, is located in the cockpit. So there's one for each pilot. So the plane banks up to 35 degrees before anyone notices banking, and only because the bank alarm went off. So the startled pilot performed a series of wild efforts that make things worse. Just 1 minute, 19 seconds after takeoff, the plane banked 55 degrees with an altitude of 2,700 feet. The plane got up to 2,900 feet before it spiraled into the ground, just 1 minute, 42 seconds after takeoff. The 52-year-old captain had deficiencies noted during recertification exams. He was poor at adherence to procedures, cockpit scanning, situational awareness. He was supposed to confidently scan the instruments. Why couldn't the pilots notice their world was tilted 35 degrees? Well, it's basic physics. So a 100-pound man is standing on a scale of elevator. The elevator is accelerating up 16 feet per second squared, which is half normal gravitational acceleration. The scale is going to read 150 pounds. So read its weight plus 50 pounds of mass times acceleration inertia. So acceleration creates inertial forces. Technically, it's not a force, it's the inertial term, it's a mass times acceleration term. So inertia is a property of matter that resists acceleration. So if you accelerate up, there's going to be a mass time acceleration effect pointing down. But you can read on the scale as a force. Acceleration is also change in velocity over change in time. But velocity is a vector. So you can have acceleration can occur with changing speed, direction, or both. Circular motion occurs at constant speed, but there's acceleration because of constantly changing direction of the velocity vector. This weight at the end of a string, if it's swung fast enough, you can break the string, which is actually pretty analogous to snapping the wings off with excess G loads. So there's a centripetal force that points towards the center, which creates a centripetal acceleration equal to velocity squared divided by radius. And the centrifugal force, the inertial effect, the equal and opposite effect that resists the centripetal force is the mass times acceleration that pulls on the string, or it gives the string its tension. So if you're turning in a car, there's a sideways shove, you can feel turning. If you're banking in a plane, so this is banking in a horizontal plane, you have the centrifugal inertial effect pointing out, and weight points down, and the vector sum of the two goes right through the pilot's spine. So there's no sideways thrust, they can't feel turning. The pilots weigh more because of inertial G loads, and so does the plane. And the wings have to supply additional lift for a heavier plane. So this is the total lift on a banked plane times the cosine of theta. That's the vertical component of lift that has to equal the weight. So the total lift times cosine theta. And again, this is for a banked plane and level turn. So the total lift equals weight by cosine theta. Let's say this is the bank angle. So the load factor N is 1 over cosine theta, which is 1 over cosine of bank angle. It's fundamental to the design of a plane accounts for the actual weightlifting capacity to overcome inertial effects of level turning. And here's load factor in various bank angles. 30 degree is a target bank angle. Airlines tell their pilots not to exceed. The defined offset was 45 degrees, so it has a load factor 1.41, which means the plane and pilots weigh 41% more. The structural limit is 66.5 degrees with load factor 2.5 Gs. The horizontal component of lift is what turns the plane and analogous to the string force. So a coordinated turn, everything turns together. You put a glass of liquid on a tray in front of you and you're banking at 30 degrees. The person, the tray, the glass, the plane all banked together. There's no apparent change in the level of the liquid in the glass apparent to the person sitting in front of it. So the glass of water appears to remain level. There's no tilt. There's no obvious tilting. In fact, there's a YouTube video of Bob Hoover, a famous test pilot, doing a barrel roll with a glass of tea in front of him.
Secretary of the Air Force, Gene Sugar, and co-pilot said, can the airplane be rolled? And I said, yes, sir. And I rolled, and the generals were all having a cup of coffee. And then I got so bold as to think that maybe I could even pour iced tea. So then we put it on them. I was getting off the thing about this. Trying to pour backhanded to see it on camera. You can see their eyes going around as the tea is poured on the glass. I had Secretary of the Air Force, Gene Sugar, and co-pilot said, and part of the airplane filled with the generals.
Watch the horizon going upside down.
Can the airplane be rolled? And I said, yes, sir. And the generals were all having a cup of coffee. I got so bold as to think that maybe I could even pour iced tea. So then we put it on film. And the difficult thing to think about is trying to pour backhanded to see it on camera. You can see their eyes going around as the tea is poured into the glass.
Did you hear any of the audio?
I can hear a little bit.
So this is our list of defined loss of control conditions. Now we discuss G loads. We could describe a little bit what needs to be outside the flight envelope. The limits of the flight envelope were established with extensive test flights and destructive structural testing. So what is the flight envelope? It combines aerodynamic and structural limitations. We make an abbreviation for annual attack. AIAA. And then apply load factor versus airspeed. So at a fixed airspeed, the only way to increase lift is by increasing angle of attack. So you keep increasing it until you limit it by stalling So load factor 1, this is straight level flight. So this is basically the minimum speed to maintain straight level flight. We repeat the process at a higher speed. So again, we keep the speed fixed and increase the angle of attack until we're limited by stalling. You can make a plot. So basically, above this curve is stalling. And stalling is a function of air density. In fact, it even varies quite a bit at airports. Worst conditions like minus 40 degrees F in Alaska, at sea level is 63% density, and Denver at 5,000 feet at 100 degrees F in the summer. In fact, typically a big plane would take off at something like 5,000, 8,000 feet. They might need 20,000 feet in Denver because the air is so thin at the higher altitude during the summer when it's hot. In fact, there's another takeoff requirement. These big tires on planes are designed for heavy loads and good periods, and every rotation will generate heat. So 20,000 foot takeoff, which is a bit abnormal, may in fact be limited by the tires instead of any other normal takeoff factors. So now we kind of complete the end load velocity, load factor diagram, AKA VG diagram, G is for G loads, or VM diagram, and N is for load factor. This is an actual flight envelope for Gulfstream. It's very similar to a big commercial jet. So here you got your stall limitation and structural limitation, 2.5 Gs. So a load factor about 2.5 Gs will permanently bend the wings, the wings will distort. There's a maximum airspeed limit. Numerous things can happen at high speed. Flutter on one example, just excessive dynamic pressure. And there's a structural limit, load factor of -1 on a negative side. A load factor of -1 could be inverted flight flying upside down on the top of a roller coaster. So we've been talking about level of turning in the horizontal plane. This is motion in a vertical plane. At the bottom of the roller coaster, the inertial loads push into the seat. The top of the roller coaster, you're pushed out of the seat. So this would create a load factor of -1, 2, flying on top of the roller coaster. So the flight envelope is based on level curves in one plane. It could be any curved plane. So this is inside the flight envelope. So you're limited by stalling on top, by structural limits on top and bottom, and maximum airspeed on the right. This is a NASA video showing destructive flooding.
sell 85 much.
So this is a very rapid destructive mechanism, flooding. It's mostly an engineering, solved engineering problem, but they can still get surprising test flights once in a great while. The increased airspeed adds more aerodynamic due to the structure. There's insufficient damping, the vibration increase until destructive failure. All surfaces can flooded. The wings, horizontal, vertical stabilizers, the control surfaces, rudder, elevated, ailerons. And this used to be very dangerous test flights. Before they had so much analysis, the procedure was to explore and inspect the flutter speed by gently increasing the speed. And if it starts to flutter back and off, it assumes you have enough time to back off. I actually saw a flutter on a commercial flight. It's my habit to sit and stare at the flaps during takeoff and landing. And about one end of the flaps is obviously something disconnected, some fastener is not connected properly. One end for a foot or two is vibrating up and down by a couple of inches. I reported to the flight crew. In addition to test flights, so that's a big part of the test flights, to verify flight envelope is safe as designed. We also verify the flight envelope with destructive tests. So if the structural limit is load factor of 2.5, which permanent bending or yielding occurs at, the destructive limit is a safety factor of 1.5 times the 2.5 equals 3.75, which means the wings are expected to snap off at a load factor of 3.75. And they actually do snap the wings off to verify the flight envelope. This is my estimate of when the wings snapped off of a Boeing 777 with about 24 feet of deflection. There is a video in the show. Did you hear that?
No, it's a microphone.
What?
The microphone.
You see, is the microphone going to the speaker should be side.
And specially built for the purpose. Just attach strong cables to the wings that pull upwards until they broke. As the test progressed, the force on the wings became so strong it caused engineers hoped that the wing would stand 150% of the strongest forces it would ever meet. With a deflection of about 24 feet before the break.
The tension in the wing increased. A crowd of observers, including many of the people who had lived with the plane for more than 4 years, fell quiet.
Ignition 15 and 75 seconds, starting the ramp now. Attention, we're now loading to 130% of design limit load. The ramp rate is again 75 seconds.
Although he was no longer the leader of the team, Alan Mulally was also there to watch. The test was a success.
154.
So Boeing traditionally snaps the wings off. They're not required to actually do that. They're just required to verify they meet the 1.5 mandated safety factor and the 2.5 G load factor. So their wings broke at 154%. The additional 4% could be certification for a stretch version of the 777. You could sneak in 10 or 20 feet of additional fuselage. Actually, we kind of look at what those numbers are. I look at the Airbus A380. So the design rules work in the sense that the wings are never falling off and not generated to the initial jet. So in 2005, the Airbus A380 failed its wing structural test. And this is failure of a very mature technology, FAA finite element analysis. The wing failed at a test of 145% instead of 150%. European regulators allowed us to add 66 pounds of reinforcement in lieu of retesting. Of course, that 66 pounds is justified based on more finite element analysis. And we can make some numbers on what this looks like. The maximum takeoff weight for the A380 is over 1.2 million pounds. So they could have derated it and accepted a lower takeoff weight. Of course, their customers would be accepting, but we're just kind of making numbers to see how significant the numbers are in terms of weight certification. So they could certify for 5% divided by 1.5. They can certify for 3.30% less, which would be 42,000 pounds less. They can use the same plane and just alter the maximum takeoff weight, which they could easily do with less fuel or less passengers, which of course the customers would be happy about. So basically, 66 pounds of reinforcement, the wings increased takeoff weight by 42,000 pounds. So that's kind of illustrates the significance of these numbers. So just 4%, 154% for a Boeing 777 instead of 150%. It easily accommodate a stretch version. You had 10 or 20 feet of additional fuselage. Really doesn't weigh that much. It's really just nothing except sheet metal and a poster of plastic in the fuselage. The A380 also has fatigue problems after just 1,600 flights. Maybe it's related, maybe not. That's a complicated engineering question. But it's unusual. I've never heard of a big plane having fatigue problems and wings after so short a life cycle. We changed the stronger aluminum alloy. Airbus's explanation is an improperly considered assembly and thermal assembly stresses and thermal expansion stresses. Again, the design rules are based on level turns in a fixed plane, and upsets are far more complicated. It's upsets kind of undefined flight, constantly changing turning planes, rotational orientation, speeds and accelerations. CFD can't do stalling for one axis rotation. So basically, the CFD can't do stalling. And this is a simplified case because you just rotate about the z-axis here. And again, upsets are kind of undefined three-axis rotations, far more complicated. And they're really beyond analysis. Plane gets out of position, falls from the sky, kills 300 people. CFD computer simulation has nothing to contribute. Recovery not studied except for initial minor deviations. In fact, in 2014, the FAA passed new rules mandating all simulators fly deep in the stall within 5 years. This would be a massive engineering problem. We'd have to re-engineer all the simulators. We'd have to justify the new designs with CFD and test flights. And it's a much bigger problem. For example, there's not a 737. There's all these different models of the 737. You have to do all the CFD and test flights for all of these planes. Deadline came and nothing happened. So basically, they failed to update the simulators. And I consider this a failure in modern computational fluid dynamics, CFD. So test flights verify the flight envelope. They analyze and test hundreds of combinations of turning, climbing, descending, acceleration, deceleration, combinations of control positions. But they do not analyze or test upsets. The simulator flies up in pending stalls. They do not fly into stalls. That was the new rule, the new proposed rule, that the simulator fly into stalls deeply, so pilots could train more for recovery. The crash investigation and the flight envelope is sometimes a factor. Crash report studies crash scenario with the simulator. If it fits, it's really rarely done. We'll also state no simulation conditions outside the flight envelope. So the flight envelope really designs normal flight. It's designed for standard flight. We're very happy with CFD for design for normal flight. My point is we kind of have no idea what's going on with upsets. And again, you have to think about those three-axis rotations. The position of the plane's kind of undefined. The crash investigation is totally based on why the flight envelope was succeeded. There's no attempt to study recovery or CFD simulation. So we can't model aircraft flow, airflow, and upset. Maybe it's just me, but I'm very skeptical about complex models. There's a complex model I kind of question there. Here's another example of a loss of control accident. The Indonesian Aviation flight 85 crashed in 2014. The Airbus A320. It disappeared 43 minutes after takeoff. They were able to recover everything because the water is only about 100 feet deep. So this is my version of the general statement of what's going on with loss of control. Computer oversight lost by another random sequence of events, and the pilots respond badly. The computer oversight seems to be lost by literally a zillion random events. This is just another example. All planes have a rudder travel limitation unit. It basically limits the travel of the rudder at high speeds. So what this is trying to show you a maximum deflection of 25 degrees up to 160 knots. After 160 knots, it gradually reduces to 3 degrees at 360 knots. So if you deflect the rudder too much at high speeds, you'll do structural damage. So the RTLU prevents excessive rudder deflection at high speeds. So the rudder travel limitation unit failed as a fault message 4 times in 50 minutes on the accident flight. The electronic centralized aircraft monitoring ECAM triggered a chime and a master caution and a message RTLU failure. So they read the ECAM instructions to turn on the flight augmentation computer off and on. So basically it's only reset another computer system reboot. So they're doing this like 3 times in rapid succession. So the RTLU failed. Again, this is the rudder travel, but everything else still works. The rudder controls the autopilot and throttle work normally. The stall protection on the Airbus is intact. The rudder is in the last position when failure occurred. It turns out to have bad solder joints in the circuit boards. So they found solder cracks. This is from the accident plane. It's a kind of news that looked there. Because Airbus has issued 3 reports addressing 2 cracks in the solder joints. One in 93, another in 2000. This is the 3rd one, 2015, after this accident. So these are the number of failures in the accident plane. 23 occurred in 2014. It's a rapid increase in the accident. So basically, the repeated failures should have triggered proper repair, and improper repair is considered a factor in this accident. After the 4th failure of the RTLU, the pilot deviated from the standard procedure and reset the flight augmentation computer circuit breaker, something we saw recently on the ground. This is not described in the flight manuals. It's not an approved procedure. It's okay to do it in the ground, but not in the air, and the pilot didn't know that. So this is not an approved Airbus procedure. The report included a non-critical malfunction of the rudder control system, resulted in a non-standard reset of the onboard flight control computers. Here's the autopilot, and auto shut off with an alarm. This is what the YouTube video.
struggle to lose weight, you must see this.
So that's what happens when the autopilot and auto thrust shuts off. Airbus A30. Words from Airbus normal law to ultimate law, and stall protection is lost. The pilots must fly manually, which is the common issue with loss of control accidents. Again, the computer is flying the plane. The computer oversight is lost for silly, random reasons. The pilots respond poorly. They're supposed to be able to fly, but they have a problem, it doesn't work out. So the autopilot is off with the rotor deflected 2 degrees, causing a 6 degree per second roll. No pilot responds for 9 seconds until the plane rolls 54 degrees left before the pilots notice. The circuit breaker shuts off the stall protection. 23 seconds later, the first stall alarm and buffet. The buffet is turbulent air created by a stalling wing. So the turbulent air makes noise, but that turbulent air flowing in the structure of the tail also creates vibrations that make noise. "21 seconds later, the second stall alarm and buffet become permanent until the crash. Now this Airbus plane, the stall alarm goes off at an angle of attack at 8 degrees. So they're apparently flying straight and level. There's no roll. The wings are level at 29,000 feet. So they're flying forward at 100 to 160 knots. It's varying. Problem is, they're also sinking at a sink rate of 12,000 feet per minute. So if you add the horizontal speed to the sink rate, the actual direction of flight is this, which makes the angle of attack pretty large because the plane is level orientation. So the angle of attack is always relative to the direction of flight. This horizontal line is the orientation of the wings. Here's the direction of flight, and here's the angle of attack. It's this massive sink rate of 118 knots that gives the direction of flight. So the procedure to get out of a stall is to lower the nose. So they're essentially in a dive. You have to lower the nose, which violates all common sense because they're going to appear to put you steep in a dive. But this is fundamental pilot training. They're supposed to understand this. If you're at high altitude, you have enough room to lower the nose. It could be a serious problem if you're too close to the ground. So the angle of attack is constant up to 40 degrees until they crash. Remember, the stall alarm goes off at 8 degrees. So shortly after 8 degrees, that's the actual stall. We looked and see what that was. There's also an engine effect with the orientation of the plane. If the engines are below the CG and you increase thrust, that's going to pitch the nose up and increase the angle of attack. Thrust reduction will pitch the nose down and lower the angle of attack. Again, the pilots are supposed to understand this. The stall training in a simulator is actually limited. The stall goes off before actual stall. So training is based on recovery of post-stall, not stall recovery. That was a whole big deal about redesigning the simulators to fly deeper in stall. So the simulators really don't fly stall. Big plane pilots really don't experience stalling. All their training is based on approach to stall when the alarms start to go off. So the typical simulator training, if they start a straight level flight, they slowly reduce the speed and increase the angle of attack slowly to compensate for slower speed until the stall alarm goes off. The procedure is to lower the nose, so this is what they practice in the simulator. Small plane pilots actually get to actually stall the plane more than big plane pilots. It's kind of not considered safe to stall a big plane. Back before the simulators got so good, they were killing more pilots in training by procedures that they now simulate than they were killing in actual accidents with passengers. There's a video of an actual stalled 747 out there. This is a live video occurred in Afghanistan in 2013. So this 747 is configured as a cargo plane, hauling 5 heavy armored military vehicles, 160,000 pounds of cargo. And they're improperly lashed. They should have 60 straps. They only had 24. It's actually a complicated problem of statics because you can't push a rope. Rigor do not consider angles and the tie down locations. We really needed a computer simulation of 60 straps that could only pull and not push. The preferred procedure is to put everything in special containers that are designed to lock to the floor. So the locks can take loads in all directions instead of a strap that can only take direction along this, or the force along the direction of the strap. This is an example of a cargo that's probably lashed. And here's our video. The fire damage was so severe, they don't know a lot of what happened, but the worst case scenario is all vehicles shift back 12.5 feet. It's just the CG 6 feet behind the certified limit. And Boeing estimated this was still recoverable. So they think there's damage to the elevator hydraulic system. Impact that sprays fuel. If you impact hard enough to spray fuel, that typically becomes a fireball because the fuel is sucked into the engines and is ignited in the hot engine parts. That's actually one thing that's less safe than a piston engine. There's nothing sucking fuel into the piston engine. So the fireball is actually a subsonic explosion known as a deflagration. And here's the aftermath. It's kind of a shadow of the plane. The sheet metal fuselage is only like 60,000 for the next tip. So it doesn't take much to bring it all up. There's 3 ways to die in a plane crash. One is excess G loads. Nazis were studying G loads that crush your spine. Because when they start doing high performance jet engines, they're concerned if a pilot ejects out, he'd be sliced by the tail, cut and kill him. So the idea is they have to eject up fast enough to avoid the tail and create compression in the spine, initial compression loads. So they were concerned about those limits of crushing the pilot's spine, and they did destructive tests of people and decided 25 Gs would crush your spine. FAA rules still mandate crash testing of seats, which is a heck of a lot easier than crash testing an entire plane. And the design limits on a crash dummy sitting in the seat during a crash testing is 1,500 pounds. You put a load cell in the crash dummy's spine, and you can't read more than 1,500 pounds during a crash testing. That's based on 25 Gs. So that's kind of a hidden secret. You got FAA rules based on Nazi test data. So that's one way to die in an airplane crash. Another thing, you need to go into space. In other words, the people aren't crushed. You need volume they can survive that. And you have to survive any post-crash fire. So this crash met all 3 criteria. People on this planet essentially died 3 different ways. We could have died 3 different ways. The Air Force did a study of pilots who ejected and concluded 70% of them had spine injuries. This is a live injection by a U.S. Thunderbird during an air show. Everyone lived, including the pilot. Only because of the angle, it looks like he was over the parking lot. He really wasn't. But he shrunk 2 inches, which came back. He went to the hospital for observations. His wife showed up. He got up to hug her, and she was 2 inches higher. He was actually 2 inches shorter. So the reason the Air Force can't prevent all spine injuries is you're pulling G's 2 different ways. You're pulling out of the dive. The G loads depend on the B squared over R of the plane's motion. And you're also pulling G's ejected with the ejection seat. This particular accident was an Untitled Chapter. They're opening up the air show with a dramatic dive. And it turned out he wasn't as high as he thought he was. Fortunately, we kind of instinctively figured that out at time enough to live. So if you eject up, there's an inertial load compressing your spine. Same thing, we talked about guys standing on an elevator, on a scale in an elevator. So same as crashing down. You crash down, the inertia of your body's weight continues down. In both cases, they're compressing your spine. So the limit on accelerating up is the same limit on crashing down. Next, I want to talk about Air France Flight 447, crashed in June of 2009, an Airbus 330. And it's really essentially the worst example of bad reporting I've come across. One of the things I do is I try to tell the story of a particular crash by looking at news reports, and they kind of wobble and evolve. So it's kind of interesting and fun. But now I have to explain, I have very little faith in it. This is one of the best examples of how screwed up early reports are. The thunderstorms in the area, we're all over that. But that's really nothing compared to what follows. Eventually, there is a connection to thunderstorms I'll get to. You have major papers in the United States, Los Angeles Times, Boston Globe, Chicago Tribune, reporting naked bodies recovered. So think about that. You got American newspapers reporting incorrectly about bodies held in secret in Brazil. Now, naked bodies are very significant. You fall from 30 feet, the wind blast rips your clothes off. So naked bodies mean the plane broke up at altitude. And that's very significant because there's a short list of things that break up planes at 30,000 feet. So here's some examples of speed falling through space. Spread Eagle skydiver has a terminal speed of estimated 120 miles an hour. Believe it or not, there's a new sport called speed diving, where they race to get the maximum speed. You head down and dive in position. You reach speed to something like 300 miles an hour. So the tumbling speed is somewhere between these two. I don't think it's ever been measured. And here's an extreme example, 127,000 feet. This guy parachuted reached a speed of 843 miles per hour. Now, air density is obviously another big variable. So here's a few things that can break up planes at 30,000 feet. Metal fatigue and explosive decompression. Basically, you got a fatigue crack growing every pressure cycle until it reaches critical length, and it pops like a balloon, sticking a needle into a balloon. In the case of the balloon, the critical length of the crack would be the size of a pinhead, or the pinpoint. And there's examples of the rapid fragmentation of the plane into 3 or 4 pieces. There's even examples of pilots being cut off in mid-sentence as the entire plane fragments around them. Now, this plane didn't break in two, but it should have. They safely landed, everyone lived except one flight attendant who happened to be close to the blast hole. But this plane should have broken too, so it's kind of a dramatic picture of the effect. You can have a fuel tank explosion, which is what happened at TWA Flight 800. This is a simulation of the explosion. So the official report says there's bad wiring that arc in the fuel tank. Not loose fittings, that's just bad wiring. Basically wiring with damaged insulation. XF's G-loads, a commercial jet is not a dive bomber. There's examples of planes and dives starting to shed parts. I don't think that crashed the plane, but obviously if you start to shed parts, you're being less safe. And of course, the terrorist bomb. So that's really about it. If you break up at altitude. But if you crash in the ocean, you got all these loss of control things, which could be a zillion things. So back to bad reporting. New signs that Air France jet broke up in flight, New York Times. Crash jet split into at high altitude. London Sunday Times. It's highly likely a bomb went off, London Daily Mail. 31 days after the crash, French jet hit ocean intact, officials say. Now, you expect the officials to be very careful about what they say. If they change their mind too much, nobody will believe anything they say, which is a good thing. That has happened once or twice, but normally, once the officials say, you can rely on it. Which is very different than unnamed sources. You have widely scattered wreckage and bodies on land. It most definitely means a breakup at altitude. But the unnamed sources reporting breakup at altitude for Air France 447 didn't understand ocean drift. It was 5 days until first recovery of 2 bodies and bits of debris. So that's 5 days of drift. And recovery continues for many days of drift. So the defined limits of recovery basically kept growing and growing, making some people think it was a high altitude plane. We also tried to do computer simulation ocean drift. It didn't work very well. I think 3 different groups tried to do it. Just after a few days, they started to contradict each other. It's almost 2 years to recover the black boxes, in part because they're 13,000 feet down. At that depth, it's kind of remarkable they recovered them at all. Now, it's very difficult to search in canyons that deep. There's only 2 ways they can search. They can pull a submersible vehicle with miles of cable, and it's hard to steer something in that canyon with detached miles of cable. Or they can send down untethered devices that must frequently surface to charge batteries. So this brings me back to the 737-800 just crashed with China. It just made news this week. Damaged black boxes were sent to Washington. On May 17th, the Wall Street Journal reports breaks the story that unnamed sources state plane subject pictures of a vertical dive. The plane did what it's told to do by someone in the cockpit. So again, this is unnamed sources. I don't know if it's correct or not, but if you ask me, We put on a scale of 1 to 10, the unnamed source reporting that turned out to be wrong, and after that, go for a 7, would be a 9 or 10. This is only, if this is wrong, it's only a little bit wrong. So as far as I'm concerned, there's plenty of room for this to be totally wrong or totally right. Totally wrong happens an awful lot. So back to advanced profile 7, what happened? PO2 measure airspeed failed and shut off the computer oversight. Again, it's one of these random events that uses computer oversight and pilots respond badly. The pitot tubes are normally seen sticking out of planes. They only got them circled in a big jet. The Airbus computer prevents pilots from stalling the plane. But the computer can't fly the plane without airspeed measured by pitot tubes. And again, this is my definition of the generic problem. Computer oversight is also very random reasons. And a couple of examples I've given here kind of leaves the impression there's a lot of things that could go wrong. And the pilots respond badly. With 30 million flights a year before COVID, I'm going to assume computer oversight is lost hundreds of times per year. I don't really know, I'm just making up a number. And I'm going to assume the pilots mostly respond correctly. I don't know any statistics on these conditions. So it's a combination of loss of computer oversight and bad response from the pilots. Each new generation of plane has more sensors and more computerization and more computer oversight. And they're definitely safer, although we recently had an example of less safe with the 737 MAX. Hopefully in a few years, we can make the claim of being safer too. There's a concern that pilots are forgetting how to fly the plane. So a lot of people are starting to talk about it. So the pitot tubes are intermittent freezing, unfreezing, and refreezing. Airspeeds are accurate or not, they're bouncing and out, correct or not correct. Autopilot's on and off. There's alarms going on and off. So how long have they been flying planes in freezing conditions? Why can't they make pitot tubes that don't freeze? Can't they make the pitot tube heaters bigger? Well, Airbus and Boeing, for that matter, they have some micromanage everything sticking out of the fuselage with drag and power usage. So in the order is placed for the new pitot tube design, there's going to be strict limits on drag and power. Presumably, most everything operates on the design limits. And they used up, presumably, the heaters at the design limits of size and power. So it can't be made any bigger, so it already is bigger. So why are they still freezing? Well, there's just too many variables to keep track. This rain, sleet, snow, hail, ice, they're all different things with different crystalline structures. The water content of snow varies tremendously. From 1 cubic inch of water equals 5 to 50 cubic inches of snow. Here's a plot of common ice crystals. This is basically water saturation density versus temperature of different forms of ice crystals. And here's a few examples of different ice crystals. Needles, whatever that is, hexagonal plates. Rain variables Rain is very statistical. What's the water contact with volume? What's the particle size and distribution? All have statistical distributions. What's the swept volume? How much rain in contact? Water interfaces differently with the surface. It's a matter of adhesion versus cohesion forces, which is adhesion is the forces between water and the surface. Cohesion is the forces between different water molecules. So water can wet the surface or it can beat up. You can actually see both on a car surface, depending on how polished it is, how clean or dirty. So if they do extensive testing, they test lights and wind times. The problem is how do they figure out to identify the worst combination of circumstances? And super cool water is another big problem, which is what occurs in ice storms, which I assume you don't have out here in California. But it's water below its freezing temperature, and it freezes on contact. One simplified explanation of surface tension and cohesion forces form spherical water droplets that resist crystal formation and freezing. So once upon contact, you disrupt the surface tension and it rapidly freezes. So you've got all these variables going on. Temperature, water vapor density, velocity, velocity, droplet size, distribution, droplet size. Because of this accident, some other events, historically, ice has been a problem all over the plane. Fuel systems on wing surfaces, and instrumentation. So the FAA sponsored fundamental research on icing, and they introduced new icing rules based on additional research. But users say they now have the worst combination. The same problem repeated. Hopefully it's better, but who knows? So back to crashing Air France 447. 8 minutes after the captain leaves the cockpit for a man-made test, the alarms go off and the autopilot off. Already showed that YouTube video. Pilots are freezing and freezing and refreezing. Stall warning went off twice. Showed that on YouTube video later too. The pilot's flying over steers a plane by excessive rolling right and left. Now my theory is excessive oversteering. I'm not a pilot, so I'm not sure I'm a opinion. I can imagine driving a car and trying to steer it to avoid a collision. You turn the wheel and nothing happens, so you don't understand what happens. You panic and you just turn the wheel more. You just turn the wheel more to look and to see a response that you can understand. So that's my theory of how this occurs. I don't think there is an official theory because it's hard to create the correct circumstances, which is a big plane in danger of crashing and create that kind of panic in a pilot's head and test his response. So the pilot monitoring says the plane is climbing a mass flow descent. 45 seconds of the event and China landing. Senior pilot arrives 52 seconds later. This increases throttle takeoff. Stall warning sounds for 50%. Stops briefly and sounds again until they crash. Senior captain walks in and says, "What are you doing?" Response is, "I don't know what is happening." The correct pilot action is nothing. The plane was flying straight and level. They should just keep doing that. And technically, they had enough information to do that. But with all the alarms going on, they're confused. Again, I'm guessing who has an experience in computer school if you have no idea what it is. Once you convince yourself it's a computer error, you don't trust anything. Again, that's just me making things up. The official report says there's no known reason why the 3 experienced pilots would maintain straight level flight. There's actually 3 pilots for a line crossing trip. So they recorded buffeting, which occurs during stalling. So I think I mentioned this, now I'm going to show you it's a faucet. Buffeting noises are noisy turbulent, and the second source of noise is air shaking the tail section. So if you turn on the faucet on, the flow flows. The flow is transparent and quiet. If you increase the flow rate, the chaotic flow turbulence changes the flow to opaque, and it becomes noisy. All that chaotic turbulence creates noise. It's very easy to notice playing with the faucet. And again, I keep showing you this video. The stalling flow, that turbulent air flowing over the tail creates vibrations that creates noise. Historically, shaking the tail vibrated the control column, giving the stall warning to the pilots. That was kind of part of the feel of flying a plane. Pilots were supposed to understand this stalling response and respond accordingly. So Boeing artificially recreates the effect of a mechanical stick shift. So they start to shake the stick at impending stall over before the stall. Well, they basically enact stick shaking when they think the best time is to warn the pilot. Airbus does not have a stick shaker. But remember that computer oversight is supposed to prevent the pilot from stalling the plane. So we believe that when working is better. Airbus also has a stall alarm. And kind of 2 different fundamental approaches to stalling between Boeing and Airbus. So the computer's pilot oversteers the plane, rapidly changes the compressive climate wall to dive and stall. It's the same situation. Because of the high sink rate, the direction of flight creates a high angle of attack. So you need to lower the nose to prevent stalling, but you can put the plane into a deeper dive, which is totally non-intuitive, but experienced pilots are supposed to understand. And they have enough information in the artificial horizon to understand the orientation of the plane. The senior pilot displayed the speed plates, which is kind of unusual. Nobody normally landing a slow plane. So this suggests he thought there's a high-speed stall. So what the heck is a high-speed stall? Well, the big commercial jets are typically flying about 0.8 to 0.86 Mach number. And since it's faster on top, there is a shock wave on top of it. Wing. If airflow's faster on top, it can become unstable. The shock wave can be unstable, disrupting the flow and lift. So it's kind of a high-speed stall mechanism. It turns out the A330 reaches over the limits first. And it's really a high-speed buffer is not an issue. It wasn't stressed in pilot training. "11 seconds before the recording stopped. Verbal alarms of pull up with sync rate. Totally wrapped at 4 minutes and 24 seconds. I'm going to start a side story back in 1932. The Army Air Corps studied pilot response and concluded 90% of experienced pilots did not maintain straight level flight without simulation. And why is this surprising? You can't walk a straight line blindfolded. In 3D space is far more complicated. And again, you got this 3-axis rotation. Once you start rotating more than one axis, how are you going to have any idea what you have to do? I'm kind of calling it undefined orientation. In a sense it is, in a sense, there's no guidance in what to do. It's undefined kind of multi-axis rotation. And we discussed you can't feel turning very well. There's all that inner spatial orientation problems. So, because 90% of the pilots couldn't maintain straight flight, they're very artificial horizon, which basically displays pitching and roll orientation of the plane. In one study, 17 of 18 loss of control accidents had no visible horizon. So it turns out dark and stormy night is a factor after all. Expect pilots to understand orientation easier if horizontal wasn't visible. Basically, a loss of control. The pilots are confused how to respond. And I'm suggesting that they see the horizon and have a much better chance of figuring it out. I'm not sure there's any easy way to test that, because again, you have to do a good job for a lot of control. It would be very confusing, unsafe circumstances, and test the pilot's response. It's never considered a factor because the artificial horizon is enough information for professional pilots to respond correctly. So they'll know it's the darkest time of night. But they won't blame that directly. But in one loss of control study, they did make a point of it. So here's the fragmented wreckage on the bottom of the ocean, 13,000 feet, 2 years later. This says there's only 3% bits and pieces of floating plastic recovered on the surface. There's basically nothing to find, which probably says something about the missing plane. Now, I suppose the missing plane, a human could have landed it intact if he wanted to. But it just puts it, just allows it to fly without fuel and fall out of the sky. It's going to fragment like this. And there's an impact on 100%. So they almost gave up locating this plane. In the area they searched, they narrowed it down to, I think it was, I can't remember. It was much smaller than anything that you figure out this information. The biggest piece recovered on the surface is a 25-foot floating composite with stabilizers. And it's floating flat, which if you're searching on the surface or from the air, it's hard to see something floating flat. You can see it right on top of it, but you're not going to see it much of a distance. Everything else is basically shattered bits and pieces of plastic. Incidentally, a plane going down deep water under pilot control never survived. I'm going to get the YouTube video that actually shows them quickly. I'm talking about deep ocean landing, not that thing that happened once a day. Once a river, the plane never sunk, the water was so shallow. The graphs double as slides. We talk about airworthiness, fireworthiness, crashworthiness requirements. Well, there's also seaworthiness. You have some of those sea trials to meet all those seaworthiness requirements. So planes ditching in the ocean was pretty common in the 50s. And most of them had good outcomes. It happened more in the 50s as a piston engine had terrible reliability with respect to modern jet engines. In fact, this was kind of a hooked in the system routine because Coast Guard kept a cover on stations just hanging out permanently halfway between Hawaii and California until the mid-70s when they finally stopped doing it. So it hardly ever happens today. People have forgotten it is in fact survival. So the pilots under the planes under pilot control is kind of perform a safe landing. So the last mostly successful water landing was a Boeing 767 occurred in 1995. The pilots fighting controls suicidal hijack. They also on the fuel engines named after as a hijacker commands. And then they fly somewhere they would fly to. Now there is a strategy of ditching in the ocean. And one of the biggest problems is the fuselage breaks and spills passengers in the water and they drown before they get in the life field. So the ideal situation should be fly with the waves, against the waves, if the swells are small enough, it'll be okay thing. There's therefore flying no just up increase on its great. So this hijacked plane, which I haven't used for the unusual water, it tends to be a bend. Engine strikes a cool here. Parts of the broken fuselage sink rapidly. Life preservers are also a factor. They tell you to wait, put it on, but don't inflate it till you hit the water. Inflate it on the plane, they dig up too much volume, and it repeats. People get off the plane. So that was a problem on this plane. So about 1/3 of 50 passengers died.
Hold on, let me.
What are we trying to do?
And the network. Yeah,
Okay, let me,
it's okay now.
okay. I have, actually, I have Wi-Fi, or I have, it might be easier.
This is what is called
It has,
5G. That's okay. We have the. Yeah. Yeah.
Times turned very bad for these beachgoers on the Comoros Islands when sunbathing turned into life-saving.
Is it using the, is the battery low? If you hook up to. I think it's time to ask for questions. You don't, the professor, I think it's time to ask questions. He will try to pull that video back, but I think it's time to ask.
Okay, they tell me to schedule calls to ask for questions. You can't make that YouTube video. It's about a 30-minute, very good show of the plane crashing. And fuselage and break. I do want to mention sections to my aviation going on the fuselage. Also passengers who have the favorite we'll play that video when Mike help put it back. So now if you have some questions, you can ask the professor. Okay, any questions? Retrieve the video. I have the first question. When you mentioned that some of the video mentioned FEA, the issue of finite element analysis. Then you mentioned the CFD. Are you referring these two are the same thing, or is actually two different issues? Well, no, they're two different things. Although actually, for things like flow, they do link together. They do a CFD of the airflow, do a deflection of the surface. So it can't be like two separate things. You cannot mention. Okay. Finite element analysis is obviously very old technology, and then it's like aerospace structures, and still not allowed for airplane design. It's certified and tested. It's got a certified computer model within 50%. So once you do that, then it's start looking at the test. JC has a question.
Do I talk into the mic because it's being recorded?
Yeah, the mic actually is here.
Oh,
That's
okay.
for the professor.
Okay. So yeah, you might want to speak a little closer into your mic. Hold it closer to your mouth. Thank you. So question, I mean, I do a lot of work in the semiconductor industry and you know, I've worked in a variety of fields where I've had to deal with lightning strikes, where lightning strikes are introducing latent failures. In other words, you know, you will see that semiconductor electronics have some type of ESD, internal chip damage. It could be an FPGA, it could be something else, could be an IO structure. And consequently, 6 months later, a year later, whatever, you know, you have intermittent issues or reliability issues and things fail. Now in today's modern airplanes, you know, you're a composite skin. So, you know, when a lightning strike hits, it tends to burn a hole in a certain region, and that charge is not distributed over the whole airplane, which kind of causes another area of reliability. So my concern is, are you aware of anyone in the aviation industry that, number one, they're looking at, you know, as gate geometries keep getting smaller and smaller and smaller all the time, we're more susceptible to single event upset issues. Single event upset issues occur at, you know, 30, 40, the higher the altitude, you know, the more the SCU event occurs. It's also more of an issue for smaller gate structures and higher density structures. And, you know, an FPGA that works fine for 6 or 7 years, all of a sudden might have some strange behaviors or results that occur down the road. So is anyone, number one, looking at safety of the electronics in a composite airplane that occur, you know, latent issues? They show up 5, 6, 7 years later from a strike that happened earlier. And B, number two, single event upset issues that can affect the airplanes. Each generation of electronics gets smaller and smaller gate structures. So we really don't know if all these control mechanisms are going to be reliable down the road.
I didn't study electrical damage from lightning strikes. But I know they have extensive FAA mandated testing for lightning strikes. And it has to prove equipment. So I don't understand why those, whatever they do now and still apply. I know Boeing had to do qualifying the 70s. The electric flows differently. The graphite fibers still electricity. So the problem is it's different. We still have massive flow of electricity from the lightning strike. I know they have all massive problems, but everything's proprietary. We don't put out details. You get something that is backwards crash and you'll see them say something. Because they don't want us to say anything about the competition. So the lightning strike that normally, I don't know why it'd be that different than what they've been doing for decades.
Again, it's the conductivity of graphite fiber is much lower than carbon fiber, so you don't have the protection that you would with pure aluminum.
Well, I didn't come across any electrical failures crashing airplane. You also have to admit I was.
Okay, thank you.
Ronald, you mentioned something. Do you have any questions, Ronald? Do you want to speak? Ronald? All right, if not, if no more question here, Professor, do you want to play that video? You want to play that video? Because we have the room till 2 and the professor and Mary need to eat, so.
You want to talk anything at all about MHA at 380?
Yeah, what professor, you want to show that video?
Oh.
In meanwhile, you can start to eat. But keep it the one for professor. And Mary, you're welcome to. JC, I'm sorry because you didn't order. Next time, let us know. Order early in advance. Yeah, basically, Ronald online, he's saying this is a very exciting presentation. Very interesting presentation. So Robert and Ronald online, if you want to say something, you can just unmute your mic. We are basically right now in a networking session. Professor is trying to show the crash video. Then we casually, if any question, we'll chat with the professor. Yeah, because we have the room for another hour, the professor need to enjoy the lunch. Yeah, the right is for 4 persons, so you can share this with the professor. Each well, this I think this is for you. Yeah, professor. That's right.
Times turned very bad for these beachgoers on the Comoros Islands when sunbathing turned into life-saving. International drama ended just 100 yards from the sand as a hijacked plane ran out of fuel and crash landed just 100 yards offshore. And it's a group of vacationing doctors help pull the injured passengers to the shore. Lives of 48 people were saved due to the heroic efforts of these vacationers.
Ah, very scary.
So that is highly survivable. Only 48 about 150 survived. But the issue is once we drown in the give them rest, and give them the food, give them some of the plane, all their life is in it's one time evacuation. So the issue is being spilled in the water. The flow breaks underneath you. Decompression is your seatbelt on. You take your neck and back and front. As bad as I look, it's supposed to be survivable.
Thank you, Professor. It's very good. I know you have a lot of more, but you need to eat. We have the room for another hour. Yeah, so we thank you so much. Thanks, Professor. It's a wonderful presentation. Today, our session chair, Dr. Michelle, signed an appreciation certificate for you. But I know you are on the trip, so we'll mail it to you, so you don't have to carry it.
Yes, thank you.
Yeah, thank you. Thank you so much. So please enjoy the lunch. So if you anything want to tell you, Professor, you are welcome. Network, but also that Professor E. We need to leave the room by 2. So I will start to pack up, but you are welcome to enjoy here. Now, this is so exciting because I know there's a lot of activities. You need to remove the file from the computer.
No. Several different things.
So you can start to wrap up. Eat first. So Mary took the kids. This is
I guess there's an extra if that.
oh, where is she? This is it. Oh, to the edge of you can see. But Professor got the piece of this. Not breast. Good. Yeah. Good. Yeah, this is coma. This is yours.
All that.
Yeah, all that. And then rice. And bottled water too. This is for you and Mary. I believe both. Yeah, then you can use the water there. All right, Ronald, we are going to wrap up, so we'll stop the recording here.
So it's interesting.